Hello and welcome to this onboarding video to the Strong Compute Instant Supercomputer, or ISC. In this video, we are going to be following the Getting Started guide of our Strong docs, which you can find at docs.strongcompute.com. So the two sections that we're going to cover are accessing Strong Compute and the Hello World training example. The third section that we've got in here, VPN, this is for folks using the Sydney cluster only, which is probably not you. So don't worry about that at all. We're just going to cover these first two sections here, and you can ignore that third one altogether. So step one is to access Strong Compute, which we start with registering as a user of Strong Compute. We have a link off to the registration page here. So I'm going to open a new tab to get access to our registration page. And I'm going to create a new user account for myself, 0826 at strongcompute.com, and give myself a nice strong password and agree to the policy and register. Thank you very much, one pass. That's going to send me an email to my email inbox where I can verify my account. So I'm just going to access that link now and confirm my account. There we go. Great. So that's confirmed. So I should be able now to refresh the page here. And now I'm inside of the ISC, inside of what we call, in fact, control plane, which is the page that you can see here. Good. So there we are. We've registered as a user. The next couple of steps that we have on the page here have to do with setting up your organization. So if you're planning on working as a team of users inside Strong Compute, then you might like to pay attention to these steps here that describe how to best set up your team and send each other invitations to join each other's organization so that you can get access to each other's resources, including credits and so on inside of Strong Compute. But we're going to move past that for the time being. The next step here as well to do with credits is how to get credits. And we have instructions on the page here about how to do that. But this is fairly self-explanatory. And for folks who are joining us for the AGI Agents Hackathon, for example, we're going to be managing the allocation of credits for you on the day. So you will not need to worry about buying credits yourself. So we're just going to skip ahead to uploading our SSH public key. So in order to do that, I'm going to go into Control Plane, visit the Workstations page, and visit SSH public keys on the left side. Then I'm going to click the Add SSH Key button, and that's going to present me with an input field. I'm then going to open a terminal, and I'm going to access the SSH public key on my machine. So I can get my public key by typing CAT. I might just make that a little bit bigger in case it's difficult to read. There we go. So cat.ssh/id_, and I'm going to hit tab to just get to the rest of that file name, and I want the file with the .pub extension, and so I'm going to grab that whole string there, copy and paste into the input field here. If you do not already have a public key, or in fact a public-private key pair set up on your machine, then we do have instructions in this Strong Doc section here about how to generate a public-private key pair. Essentially, you're running the SSH keygen command to do that. And then following those instructions. So now that I've input my public key, I'm going to click Submit New Public Key. That's taking me back to containers. So on the SSH public keys page, there we are. I can see my public key has been registered. So that looks good. Next step is to create and start a container. So I said that what I was going to do is to brush past the getting credits section. So in order to actually start a container, I'm going to need credits. And so to do that, I'm just going to simulate that by giving myself credits just now. And I'll be able to track the amount of credits that I have available on the billing tab in Control Plane just here. So if I tab to billing, I can see I have 0 credits for the moment. And I'm just going to now, if you'll bear with me 1 minute, give myself some credits. Yep, good. I'll need to just refresh. There we go. And there we go. That looks good. So now I should have, if I refresh the page here, there we are. So now I can see I've got $50 in credits, which would be more than enough to do everything that we need to do just now. So if I go back to the workstations page, I'm going to now create and start a container. So again, the instructions on this step here are in section 1.5, create and start a container. We're going to visit the workstations page and create a container and so on. So let's go ahead and do that. So on the workstations page, on the containers tab, we're going to click create container. And we're going to give our container a name. So this is going to be new container. And we can pick combinations of images and distributions. The page is going to respond as we make those selections to essentially narrow down what remains as possibilities based on our selections at that point. So once we've got a combination of distribution and image that we like, click Add Container. Containers in Strong Compute are quite lightweight, so you can create them. You can create multiple containers. You can delete containers whilst ever they're not running. And containers are associated with a particular organization. So as I've joined Strong Compute just now, I've been allocated a new organization, which you can see reported in the top right here. The organization that I'm in is called Atom plus today's date at strongcompute.com's personal organization. Let me just show you that full name here. So from the top right menu, view organizations, and here's my organization here. There is the name of it. I might just update the name of my organization actually to be something a little bit friendlier. Let's call this Atom's New Org. There we go. That's going to be my organization name. You can see the name has been updated now in that, in the menu at the top right. If I refresh, there we are, Atom's New Org. Great. So this container here is associated with that org, and all the containers that I create here, because I'm viewing the content associated with Atom's New Org, all of the containers here will be for Atom's New Org. When I belong to multiple organizations, in particular if I've joined somebody else's organization, then I will see the containers associated with that organization when I select it from this menu in the top right here. Good, so let's go ahead and start this container. I'm gonna click the start button. And for you all that are joining us for this onboarding, we are going to be working in burst workstations. A burst workstation is essentially a cloud machine that we're spinning up, which is going to have potentially some GPUs on board that machine, or possibly just four virtual CPU cores in the case of these two shapes here. And they are going to exist somewhere in the world, which you can see is described by the end of the names of these shapes here. So AWS Sydney is obviously the AWS cloud, the Sydney region. You can see on the left side is some information describing the shape of machine that we're going to be spinning up. So 1 by, 4 by, 8 by, that indicates how many GPUs are on board that machine. In the case of the 4 vCPU machine, of course, that's 0 GPUs, but 4 virtual CPU cores. And then we have L4 and L40. These are the two kinds of GPU that we have available on workstation machines, on our burst workstation machines. And then what follows is the VRAM size for those GPUs. So this would be a 4 by L4 GPU, each with 24 gigabytes of VRAM in those GPUs in our AWS Sydney region. So I'm going to actually select that workstation to demonstrate. The next option here, we don't want to touch this. So these burst shapes or cluster menus are either or, so mutually exclusive. So you select from the top menu, don't touch the bottom menu, and you're good to go. You can also optionally cache a data set to your burst workstation to work with if you'd like. In this case, what I'm going to do is I'm going to cache the fashion MNIST dataset to that workstation because it's nice and lightweight, and the idea is that we want to run through this demo as quickly as possible. So I'm going to spin up a machine that's got 4 L4 GPUs, each with 24 gigabytes of VRAM in Sydney and the AWS cluster, and I'm going to have my fashion MNIST dataset cached to that machine and available to me when I open up my container. So let's go ahead and click burst. And you can see that the status of my container has changed to starting. I've got a nice purple hue to my container. And I can track the progress of spinning up my burst instance over here under procuring instance, we can see, there we go, the progress bar here. We're now checking in with that instance, and shortly we will be running some health checks and downloading all of the data that we need to that workstation. So let's just track ahead in our docs to where we're up to right here. So containers can be started on any cluster the user has access to or on a burst workstation. So that's what we're doing here. Here's some description about burst shapes and so on, caching data sets. Good. So we're up to step here. Once your container has started, you'll see an SSH command. So we're waiting for that SSH command to appear on our burst workstation here. All right, so our container has started. Our container color has changed from purple to green to indicate that it's running. We have a status running in the bottom left, and we've also got an SSH command displayed here, which includes a port number and an IP address for a machine, and implied we're going to SSH in as root to that machine. Good, so that SSH command is displayed. The next steps are for us to essentially make contact with our machine, SSH in, and ping the cluster, ping the Strong Compute system to make sure that we're authenticated inside of our container. So let's go ahead and do that. From control plane here, we're going to click on this little button here to copy the SSH command to our clipboard. And I'm going to open up my terminal again, and I'm going to just paste that into my terminal here and hit enter. That's going to ask if I'm sure I want to connect, which I am. So I'm going to type yes. And now we proceed into our container. So now we're inside of our container, which is running on our burst workstation in that region in Sydney on AWS. So the contents of our container you can see listed here. There's not a hell of a lot in our container right now. We do have a credentials.isc file, which is what we're going to use, or what is going to be used when we run isc space ping to authenticate with the cluster, or make sure that we are properly authenticated. So isc ping, and we get success data pong, so that's excellent. So we're all set up to make contact and run experiments through the ISC. We can also do other things inside of our container. So for example, to verify that we have all of our GPUs on board, we can run NVIDIA SMI and see that we indeed do have 4 of the L4 GPUs with 24 gigabytes of VRAM on board each of those GPUs. And working interactively in the container right here, we can do all of the things that we'd like or need to do to prepare our experiments and our projects. So we can create files, for example, and all that good stuff. So let's just get rid of that for now. What we're going to do is, let's have a look at where we're going next. Good. So we have got into our container, run ping. The next step that we have here under the Access Strong Compute section of the docs is instructions on how to set up access to your container using VS Code. So this is a much nicer way of accessing and interacting with the contents of your container interactively using an IDE like VS Code as opposed to a bare terminal. So let's go ahead and do that. I'm going to close my terminal here, and I'm going to open up VS Code. So let's do that. Good. So here's my VS Code. Again, I'm going to make things a little bigger so that you can see. That's great. Now, what you're going to want to have installed in VS Code in order to do this sort of nice and neatly, and I believe the same or similar will be there for Cursor, is install this Remote Explorer utility or extension. The way that you can do that is click on Extensions and just type Remote Explorer, or Remote rather, SSH, I think is what we want. Yeah, good. So it's this guy here, Remote SSH is the name of the extension that we want to install. So I have it installed here. And now that it is, I get access to my Remote Explorer utility on the left. Clicking on the Remote Explorer utility, I'm then going to click on this little cog icon, which is on the SSH accordion bar here. And that's going to suggest from the menu up top that I open my SSH config file at .ssh/config. So I'm going to click on that one. That's what I want to open up. And here I'm going to create a config to access Strong Compute. So in order to get the details that I'm going to need for that, firstly, actually, I can give my host a name. This is just whatever I would like to alias or nickname my machine here. So this is going to be, let's say, Strong Compute. The host name is going to be the IP address from the running machine in control plane. So here is the IP address for the machine. I'm going to copy that and I'm going to paste that in over the top of the host name. The user is root. So recall what precedes the @ symbol here is the user, and that's root. So I could copy it, or it's probably pretty easy to remember, but there you go, root. And the last thing that I'm going to absolutely necessarily need here is the port number. So port is going to be 50415 in my case here. So I'm going to copy that, and I'm going to paste that in here. Great, so now my host should be all set up and ready to make SSH connection to my machine. And I'm going to click this little rightward pointing arrow here next to my Strong Compute SSH config to go ahead and do that. So there we go. SSH is now connected to Strong Compute. I've got my handy welcome message. First thing that I'm going to do is actually open up Explorer in a particular directory. So if I click open, I click this icon in the top left of VS Code or Cursor or whatever, and click open folder. It's going to suggest that I open up in /root, which is exactly where I want to go. So I'm going to leave that exactly as it is and just click OK. Yes, I trust the authors, so click yes. I'm going to get rid of Copilot. Thank you very much, but no thank you this time. And I get my welcome message back. Great, and now I can see the contents of my container that we saw from the bare terminal before. I can also get access to a terminal inside VS Code here and click by clicking this icon in the middle at the top right. And I'm just going to want to select terminal. There we are from the bottom here. Great, so now I have a terminal and I can run same thing as before, ISC ping, and that is going to authenticate again with the cluster. ISC, just to flesh that out, is our command line interface or command line tool for container and cluster operations, things like authenticating, also running experiments, tracking experiments, things like that. We'll use the ISC command. Great, so let's have a look and see. I think that is going to be the end of section 1 of our Getting Started guide. We've just run through that whole section bit there. So let's now move on to the Hello World training example. So the first step in moving towards running an experiment in control in the ISC, in Strong Compute, is to create a project because all experiments that run on the ISC happen under a particular project which you create. So we're going to go to control plane, and in control plane we're going to click on projects. And you can see I have no projects yet. So I'm going to click on the new project button. I'm going to give my new project a name. So this might be new project and create. So now I have a new project. I'm going to want to just remember that this is where I will find the ID for that project right over here. So this is PRJ, Faithful Separated Theater, today's date. So that's the ID for the project, which we're just going to need in 1 minute. Good, so create a project. Next step is to install some necessary dependencies, or some basic dependencies, I should say. Our containers all come more or less as blank slates. So we're going to need to install some basic things like Python and Git and Nano so that we can start working with the things that we want to work with. So into our terminal here, I'm going to just paste that command apt update apt install python pip virtualenv git and nano. We're going to be working with a Python virtual environment or virtualenv in this demo, which we generally recommend doing. You don't have to. You can install things straight into the container if you want to, but working with a virtual environment is just good practice so that you can quickly destroy and rebuild your dependency stack if you would like to. Good, so that's all installed now. The next step is for us to create and source a virtual environment. But what I'm actually going to do is I'm going to not create one that's called .fashion because we're not actually going to run the fashionMnist Hello World example today. We're going to actually run something a little bit more interesting. We're going to do a fine tune of the DeepSeek R1 model. So let's call it something else. But firstly, what we can do is cd to home and then create a venv. I'm going to copy that, but we're going to do something slightly different. There we go. We're going to paste that in, and we're going to call this DeepSeek. Python 3-m virtualenv DeepSeek, and then we can source that venv with source bin activate. There we go, great. So we've got our DeepSeek virtual environment created and sourced here. The next step is for us to clone our demo repo here. So rather than build our project from scratch, we're going to use one that we've created previously. So I've cloned our ISC demos repo here, and here that is. The DeepSeek example is this guy right here, or this set of files here. Good. So the next step is to install dependencies. So here the commands are for installing the dependencies from fashionMnist, but we're actually going to install instead the dependencies for DeepSeek. So the DeepSeek demo has a requirements.txt file, and here it is. We've got a whole bunch of different things in there, or not too many really, but let's go ahead and install those. So cd into DeepSeek, pip install -r requirements.txt. Oops, did you mean install? Yes, I did. It wouldn't be a demo video if somebody didn't make a typo at some point. Great, so that's installing our dependencies. You'll see that one of the things that we're installing amongst this set of dependencies is the cycling utils package. So cycling utils is a package that Strong Compute has developed for making it easier to do distributed training on a cloud cluster. But also there is a utility in that package which is essential for utilizing the Strong Compute checkpointing facility. So here is that repo, Strong Compute Research /cycling utils. We do have a whole bunch of docs here on that repo that you can read through. The important thing, as I mentioned, for saving is in the cycling utils saving.py file, and it is this utility here, the atomic directory saver, which we will see in action. But you can get into this repo and have a look at all of these description here of that utility and some example implementation, how to use it. Good, so let's go back to our container and check on how that's going. So yeah, we're installing our dependencies. While those install, we can also move ahead to, oh, there we go, that was quick, to the next step of the demo here, which is to update, and just to be sure, let's see, right, update the experiment launch file. So instructions here on how to do that. This is an example template of an experiment launch file, but in the DeepSeek R1 demo repo, we've got a whole bunch of template experiment launch files here that we can just use out of the box. So for example, today we're going to run the 1.5b. We're going to go the little baby of the DeepSeek distillation models. And here is the template for that experiment here. And recall that project ID, the project that we created and the ID for that project. This is where we're going to need to copy and paste that ID into in order to run this experiment. So let's do that. I'm going to go back into control plane, copy my ID here, open up VS Code and paste that over top of our project ID. There we go. So making sure to keep the inverted commas, but not have any other spaces in there. So there we go. That's what that should look like. Just to point out a couple of the other features in this file, the experiment name, also in inverted commas, this is anything that you want to call this experiment. So feel free just to give this a short string name that you prefer. GPUs is the number of GPUs that we are going to call on to run our experiment here. By default, we've set this to 8, but we can actually boost this up. Maybe let's do something like 16 GPUs. Typically, cloud machines that we train on are going to come with 8 GPUs per machine. So this should mean that we get a cloud cluster of 2 machines, each with 8 GPUs on board, brought into existence for training our experiment. We are going to update the compute mode here from cycle to burst. You might even find by the time that you clone this repo that compute mode comes set to burst by default. But we're going to run in burst mode. And what that means is that when we launch this experiment, we are going to call on the ISC to spin up some cloud machines, as I said, likely 2 cloud machines, to run our experiment. Enough machines critically to satisfy our requests in terms of the number of GPUs. So that's what compute mode burst means. And there are other compute modes that you can read about in our docs, but for the purpose of you guys, compute mode burst is almost certainly what you're going to want to be looking at. The dataset ID list here has 2 items. So the way this works is that in Strong Compute, we have datasets, so-called. So if I tab back into control plane on the datasets page here, you can see all of the datasets that we have in control plane in Strong Compute for you to use out of the box. And a whole bunch of those are in fact the DeepSeek R1 distill models. So that includes the 32B, 14B, et cetera, et cetera. So when we say dataset, what we really mean is a data payload of some kind. And in this case, or in these cases, we are using the dataset abstraction to be the home, or where we can host model weights that all of the users of Strong Compute can get access to out of the box in a public library. So we've got a whole bunch of different models actually that are in there like that. We've got Llama 3, Llama 4, Nematron, et cetera, et cetera. For training and fine-tuning our DeepSeek R1 1.5B model, we're going to call on the Microsoft Research Wiki QA corpus dataset, which is another dataset that's available via Hugging Face. So in addition to model weights, obviously, we can have ordinary datasets in here as well. And just to let you know, we are able to create new datasets from this page as well. By clicking on New Dataset here, we can bring in datasets that are already hosted in an S3 bucket. So you give your dataset a name, provide access credentials for your bucket, and further details for your bucket, and click Add Dataset. And you can also use this form to ingest models and datasets from Hugging Face as well. And there are docs on our Strong docs for how to do that too. So do check out that. But yeah, for now, it suffices to know that we have a couple of data sets in our ISC file here, this guy here and this guy here. And one of these is going to be the model weights for the 1.5B model. And the other is going to be the data set that we're going to fine tune our model on. To make it a little clearer what's going on down the bottom of our ISC file here, our experiment launch file, we're actually passing those in as keyword arguments to our train.py script. So our dataset ID is this one, the Visual Water Soup dataset. That's going to be the Microsoft Wiki QA dataset, and our model dataset is the plural branch bag dataset. So that dataset will contain our model weights. To say a little bit more about this last section of the ISC file here, this command. The way to think about what's happening here is that when you launch your experiment, we are going to take a clone of your container and we are going to run your container with everything that you've created in it. So in my case, that would include the ISC demos repo and any changes that I've made in here, like the project ID and so on. We're going to run your container with this as the entry point, or the running command, or however you want to describe that. Your container is going to start and it's going to run this command or this sequence of commands. So in my case, what that's going to do is it's going to source the DeepSeek virtual environment that we just created, and then we're going to use torch run to kick off a distributed training process, each running the train.py script, passing those keyword arguments. So torch run is going to be looking for some environment variables that we are setting on the nodes on behalf of you guys as users. So we'll set the number of nodes and the nproc in order to satisfy that GPU's requirement up here. Good, let's go ahead and without further ado, run this to see how this works. So yeah, good. So we're in the DeepSeek directory here. I'm going to copy the path to that. Yeah, good. So we'll go ISC train, and actually I could just run DeepSeek R1. It's the quen 1.5b.isc file. So I'm going to run that ISC train and then the path to the experiment launch file. And I get a message preparing your experiment, and then success. Preparing burst experiment. Visit control plane to launch your burst experiment when ready. So visit control plane. Let's jump back into control plane and see what it's talking about. Visit control plane to launch your experiment. Good. So in control plane, we want to actually move to the experiments tab. And in the experiments tab, we'll see here is our experiment that has just launched. So on the right-hand side, we'll see there's a button that says burst, which is currently grayed out. What that means, or the reason that's grayed out, is that the ISC is currently in the process of packaging your container, or my container in this case, shipping that to the cloud, and preparing it to be ready to download onto our burst cluster, onto the training cluster that's going to run our experiment. So as soon as that process is finished, we should see this burst button become active or available in a nice purple color. So we'll just give that a minute. There we go, great. So our experiment has finished preparing. Our container has been shipped, and we can now click this burst button here to launch that. So there we go. That's now launched, and you can see that we've got another button that's become active, last logs. When our experiment is running, we'll be able to click that last logs button and actually get back the last handful of logs that have been produced by our experiment as it's been running. This details button up the top here, when we click on that one, and that will take us through to a page where we can track on the right-hand side the progress that our experiment is making as it is starting up. So you can see here we're initializing a new attempt at the experiment. We are allocating a cluster with 16 GPUs using a particular shape. So a little bit like a burst shape, we have a number of different shapes that we can spin up burst clusters on, and we'll see more of those in 1 second. But we're allocating that cluster. Looks like here we've allocated a cluster, so that was done. We now have machines that are available, and we are waiting for that cluster to initialize. So we're running some setup and health checks on that machine right now, or our agents are busy making sure those machines are ready for us to use. Yeah, good. So those burst shapes, the first one here that you can see, that's one of the set of shapes that are available that you can find on the burst tab here. So here we go. These are the workstation shapes at the top of the page. And if we scroll down, we'll see the experiment shapes. So this will be the first one that was tried, the AWS US East 1 L4 Spot machine. It's a G6 48 large machine with 8 GPUs on board. So we're going to have spun up a cluster of those types of machines in that region in US East 1 to run our experiment on. The way the concept of an attempt works, so you will have seen a moment ago where in our burst logs it said attempting to spin up our burst cluster. The ISC is going to try to spin up a cluster of each of these different types of shapes, one after the other, Because we're spinning up clusters in a particular provisioning mode, which doesn't always guarantee that there will be capacity of that particular shape in that particular region, the ISC is just going to move down the list until it finds a shape in a region that is available. You can also, if you'd prefer, to target a specific type of machine or a specific type of shape, you can pass an additional argument in your experiment launch file, which targets a specific type of shape. So if you want your experiment run on A100s or in fact H100s, then you can pass that argument in your ISC file, and it will insist on running on those machines or nothing at all. Good, so that is still underway. Let's check back in on our experiment now. Good, so we're preparing the burst cluster storage. Shortly we'll see that experiment start to run. But while we continue to wait for that experiment to start, we can take another quick look at the project files, the contents of our project, and what's actually going to happen. So the train.py file is the first point of contact for us for this experiment. We have here the train.py file in the ISC demos repo. We won't go through this in an enormous amount of detail, but just to point out a couple of things that are going on in here that are worth noting. From cycling utils, we're importing that atomic directory saver. This train.py script is running a LoRA fine-tune of our DeepSeek model using FSDP to shard that model across all of the GPUs in our cluster. So that's a really handy technique for being able to train on or fine-tune large models up to, in this case, the 70B model. And in fact, the larger the model, just the more GPUs that you'll need in order to shard that model across. Good, so if we scroll down in our training script here, we've got a whole bunch of setup that we're doing. So this is fairly standard, initializing the process group, boilerplate for distributed training. We're loading our model, and this is using a memory efficient loading technique, moving it onto the meta device before broadcasting the parameters out to the whole model. Sorry, broadcasting the model parameters to all of the GPUs. We are constructing the PEFT modules, so parameter efficient fine-tuning LoRA modules for our model, and then injecting those into the model itself. Then we are wrapping that model in FSDP. So FSDP, fully sharded data parallel, is a technique for distributing the model itself across your GPUs so that each GPU is the home for a subset of the weights of that model. And that's a technique for minimizing your memory overhead, so you don't have to have the whole model in the memory of one GPU at a time. Good, so then we've got some data preparation details here, which I'll gloss over because they're particular to the Microsoft WikiQA dataset, but if you'd like to, you'll have plenty of detail in this script here to be able to understand and probe what's going on inside of those datasets and the shape of data that comes out of them and so on. Good, so here is where we are setting up the saver. So when we run atomic directory or call on an instance of the atomic directory saver, we pass the output directory, which on Strong Compute must be the path that's set in the checkpoint artifact path environment variable. So we pass that in as the output directory, and we also pass an argument isMaster, which should be true for only one of the ranks, only one of the GPUs in your process group. So only one process in your process group should be master, and that process should be passed isMaster equals true. All of the others should be passed isMaster equals false. Good, so once that saver is created, we are going to check to see if a checkpoint already exists. So the idea here is that in Strong Compute, we'd like to be able to move your workload, your running experiment, around the world if need be. This is really helpful and handy in the case where you have hardware failures, for example, or network failures, which occur from time to time, blackouts. Anything can go wrong, and if it goes wrong, we want to be able to take your training, your experiment, wherever it got up to, find a new cluster for it to run on, download all of the necessary data to that cluster, including the most recent checkpoint, and resume training your model. And so this code here is essentially handling that. So we're checking to see if a checkpoint already exists, and if it does, we are going to load the state dict from that checkpoint into our model and optimizer, and we're also going to load the progress that was made through our training and test data sets into our data loader, in fact, into the sampler inside of those data loaders. There are some other things that we're loading from that checkpoint as well, which are just about tracking progress and so on. So there we go. That's how that all works. Then inside of our training loop, which is doing all of the good and standard stuff like forwards and backwards and loss, optimizer step 0 grad, etc., we are going to use the saver to prepare a checkpoint directory. And then we are going to, in this case, use the distributed checkpointing utility and the utilities that we've created in this repo for distributed checkpointing to call on each of the processes in our process group to save its chunk of the model weights into that directory. And then we're also calling on one of those processes to also save the payload that contains the progress through the data loaders and those other metrics that we're tracking also to that checkpoint directory. And then when we're done, when all of the processes are done saving everything they want to save into that checkpoint directory, we finalize that checkpoint by calling saver.symlinkLatest to that checkpoint directory. All right, so all of the processes in our process group call the saver.prepareCheckpoint, and all of them call saver.symlinkLatest. There you go, including rank 0 and everything else. So once that has completed, you now have a directory which our system will detect and recognize as a finalized checkpoint and be ready to ship. As our experiment is running in the background, Strong Compute every 10 minutes is doing a sweep of your local file system to detect those checkpoints and shipping the latest checkpoint by default to our cloud storage as backup. So yeah, that's how the checkpointing facility works. We're doing a similar thing if we are, or when we do loop over our eval test as well. So let's check back in on our experiment, and great. So we can see our experiment is now running. Here are all our burst logs, which completed their process setting up for our training. The last thing that we get printed off here is burst preparation completed. Happy little message. And we'll see a green running status displayed to indicate that our experiment is running. So back on the experiments page now, like I mentioned, we can use this last logs button to get the last logs printed from our experiment. So in particular, this is the capturing of standard output from the 0th node rank. So we have 2 nodes in our cluster, each with 8 GPUs on board, 16 GPUs in total, 2 nodes. And so on the 0th node, we are capturing the standard out and dropping those into a log file. So that's what we can see here. We can see our loss is going down. That's very, very good as our steps track up. So yeah, there we go. It's training. We can get also access to artifacts from our training from the details page of our experiment. On the details page, if you scroll down, you'll see artifacts for the name of my experiment here, DeepSeek R1, Quen 1.5B. There's the experiment ID. And the one artifact type that we have on this page so far is called logs. So if I click sync to workstation, and from this menu here, select the container that I'm running and sync artifact, that is going to give me a little message to say syncing complete. Very good. And then back in my container in VS Code here, if I navigate to cd/shared/artifacts/ well, let's have a look what's inside there to begin with. Inside /shared/artifacts, we have a subdirectory named after the experiment, estimated warp cardboard, that we just ran, the experiment. So I can cd into that experiment directory. Inside of the experiment directory, I now have a logs subdirectory because we just synchronized the logs for that experiment. And inside of there, we have two files, rank0.txt, rank1.txt. Rank0.txt contains the logs, and I might just make this a little smaller now actually so we can see that printed properly. There we go. These are the logs that we just saw displayed in control plane from the last logs button. So it's made a bit more progress since the last time we checked on it. But there you go. We're going to continue to get, or rather that is the logs for the 0th node rank. The other file, rank1.txt, just contains whatever it is that we have programmed to print off on rank 1. So the fact that we get logs on rank 0 and not on rank 1, that is purely a consequence of the way that we've written our train.py script here. So in particular, where you see this timer.report, that's a utility that we've written to only print things off if it's the master rank in our world of processes. So that's why we only see those outputs printed off on rank 0. But as you're developing your training script, you can obviously feel free to print off on any process, any node, and then you'll find those logs printed off here. In particular, if your experiment fails, if you've made some modifications, run an experiment and it's failed, both of those rank files here would be a great place to go and check to find tracebacks, to find what that error might have been. So that's great. So now we have our experiment that's been running for a little while. It's made some progress. And what I'm going to do actually is just click the stop button to hurry things along here a little bit. I mentioned that every 10 minutes, the ISC is doing a sweep to check for checkpoints and to ship those checkpoints back to our cloud storage. When that happens, you'll see those checkpoints start to appear down here in this artifacts section as well. But rather than wait for another 10 minutes, I'm going to click stop for the experiment, and that's going to trigger a final cleanup sweep of the cluster for me, and it's going to trigger a shipping of those checkpoint artifacts for me before it tears down our training cluster. So in order to stop this experiment, I click stop, and then I copy the name of the experiment here, DeepSeek R1 Quen 1.5B, into the input field and click cancel. That's going to go ahead and cancel my experiment. So it's going to stop the experiment running. It's going to do that sweep of the machines, ship any checkpoints that are found there to our cloud storage and make them available to me on the details page. And it's going to tear down the the cluster that my experiment was training on. We'll see that all happen here too. There we go. So it's canceled. We've shipped back atomic directory checkpoint 4. So as our experiment was training, our model actually looks like it got through 4 checkpoints before the experiment was stopped. So our system has detected that this is the latest checkpoint and it has shipped that checkpoint back. There are other behaviors that you can set on the atomic directory checkpointer to make it ship back more checkpoints if you'd like. Again, refer to the docs. And in order to get access to those, to that data, to the checkpoint itself, I can synchronize that artifact to my workstation. So that's going to sync. I'll just give that 1 second to run. There we go, syncing complete. Great, and now inside of my shared artifacts experiment directory, if I navigate to one layer above logs, we'll see that in addition to logs, we have checkpoints. And inside of checkpoints, we have our checkpoint itself. We also have here, this is a symlink, which as you look at it now, you can essentially read this as pointing at the latest checkpoint. So if you've actually synchronized multiple checkpoints to your checkpoints directory here, then this symlink will point to the latest one in that set. So inside of the atomic directory checkpointer directory, we'll see all of the chunks of our model that were saved here. And in fact, what we've done in our training script is only to save trainable parameters, which for our LoRA model correspond to the LoRA modules themselves, but saved in a distributed checkpoint format. And there is our train state, which includes our progress through our data loaders and so on. Great. So that concludes essentially setting up our container, running an experiment, obtaining our checkpoint artifacts, and all of that stuff. So the last thing to point out, just as we wrap up, is that everything that we've done will be drawing down on our credits. So here you can see that we have reduced from $50 in credits down to $40.52 in credits. We have some pending charges. So pending charges are essentially anything that we're still currently spending money on, something that is actively incurring cost. So in particular, we have items associated with the container itself that's running and currently active. And we have some artifact storage costs as well. So those artifacts are currently stored in the cloud and we're incurring cost for those, a very small cost. You can see on the right-hand side, most of those are too small to display, much less than 1 cent so far. But yeah, we can also eliminate those pending charges if we'd like by visiting the experiments page, and on the details for this experiment, for example, click delete all artifacts or delete them one by one. You can do that as well. But here I'm going to just delete the artifacts for this experiment. There we go. And that's going to have finalized those costs associated with, finalize those costs associated with that, with those artifacts. There you go. You can see they've cleared out of pending and they'll now appear in the history. So this is the history of all charges that have been incurred on my account. Oh, and of course, the last thing that we will be continuing to incur cost for is running our container. So we can stop our container by clicking this stop button here. And that will, similar to the way that stopping the experiment tears down our burst cluster and recovers our artifacts, when we stop our container, we first recover the container data itself. So that includes all of the changes that we've made to all of the files inside of that container. We ship that back to our cloud storage, and then we tear down the instance. And there we go. So that container is now destroyed, or rather the burst workstation is now destroyed. And we can also, if we want, we can delete our container altogether. And this will, so right now what we have is data for that container stored in our cloud storage, and we're continuing to pay for the storage of that data. But we can put a stop to that as well by deleting our container. I can delete the container by copying and pasting the name of the container into this form here and click destroy container. And now we have cleared all the way back to nothing running or incurring cost anymore. Great. So that's all for this onboarding. Just as a recap, we've covered accessing Strong Compute, registering as a user, setting up with access to your container and so on, and running our Hello World training example, which in this case has actually been the DeepSeek R1 training example. Thanks very much for joining us, and look forward to seeing you at the hackathon.